It starts with a ring of light, not a star, not yet, just a faint, glowing circle hanging in the dark, photographed by an instrument built to see things no human eye ever could. At first, nobody outside a small group of astronomers even notices. Then the ring gets brighter. Then it gets brighter again. For nearly 40 years, one object has been quietly rewriting what we thought we understood about how stars die. Not in a flash, not in an instant, but frame by frame, year by year, in something closer to slow motion than anyone expected an explosion to be. This is the real story of the star Hubble has been watching die since before most of its viewers were born. The date was February 23, 1987. In the Large Magellanic Cloud, a small satellite galaxy tethered to our own by gravity, a blue supergiant star reached the end of its life. It had spent millions of years fusing lighter elements into heavier ones, climbing the periodic table one exhausted fuel source at a time, until its core filled with iron and could burn no more. In less than a second, that core collapsed. The rebound tore the star apart. Astronomers on Earth saw it almost immediately. It was the closest supernova to be observed with the naked eye in nearly 400 years, and it gave the field of astrophysics something it had never had before, a nearby, modern, instrumented view of a star's death, unfolding in real time. Researchers would come to call it Supernova 1987A. That alone would have been enough to make it famous. But the story was only getting started. 168,000 light-years. That is roughly how far away this explosion took place, meaning the light-reaching telescopes in 1987 had already been traveling since before modern humans existed as a species. The explosion itself did not happen in 1987. It happened roughly 168,000 years earlier. What astronomers were watching was old news finally arriving, and it kept arriving, for decades. When the Hubble Space Telescope was carried into orbit in 1990 aboard the Space Shuttle Discovery, one of the objects waiting for it was this same dying star. Ground-based telescopes had already spotted something strange around it, a faint ring of gas, glowing softly, encircling the wreckage like a halo around a corpse. Nobody fully understood why it was there, or why it was shaped the way it was. Hubble changed that. In 1994, Hubble's Wide Field and Planetary Camera 2 captured the ring in detail no ground-based telescope could match. Astronomers realized the glow was gas the star had shed long before it died, now being lit up from within by the explosion's outward-racing shockwave. It wasn't one ring either, it was three, arranged in a strange hourglass-like structure that still isn't fully explained. The light illuminating those rings had been fading for a decade already, and researchers kept watching, waiting to see what would happen when the shockwave itself finally slammed into the gas. Two anomalies emerged from that ring, and neither one had a simple answer. Anomaly 1. The shape itself. A normal dying star should shed material more or less evenly in every direction, producing something close to a sphere. Supernova 1987A's progenitor didn't do that. It expelled its outer layers in a strange, pinched, hourglass-like pattern long before it exploded, leaving behind three distinct rings instead of one simple shell. Nothing about a single dying star on its own easily explains why. Anomaly 2. The timing of the light itself. The rings weren't lit by the initial flash of the explosion. They were lit later, as the explosion's radiation raced outward and struck gas the star had already shed years or centuries earlier. That meant the ring wasn't a snapshot of the explosion. It was a delayed echo of decisions the star had made about its own structure long before it died, replayed for astronomers only once the shockwave physically caught up to the evidence. Researchers have proposed a companion star, since merged with or stripped by the exploding one, as one possible explanation for the pinched shape. Others have proposed rotation, or magnetic fields, sculpting the outflow into its unusual geometry. No single model has fully closed the case. Stay with me here because this is where it gets strange. A supernova is supposed to be fast, peak brightness in days, a dramatic fade over the following weeks or months. That is the textbook version, and for most of the roughly 10,000 supernovae catalogued in modern sky surveys, it holds up well enough. Supernova 1987A refused to follow the textbook. Instead of fading into darkness, the object kept evolving, decade after decade, as the explosion's shockwave physically slammed into the rings of gas that surrounded it. Bright knots of light began appearing where the collision was happening, flaring up in specific places around the ring rather than everywhere at once. Astronomers watched new hotspots ignite in the mid-1990s, then multiply through the early 2000s, as if the ring were being lit from the inside by a slow-moving string of firecrackers. By 2017, on the 30th anniversary of the original explosion, Hubble was still pointed at the same patch of sky, still photographing the same dying star, still finding something new. The telescope had by then returned to this object again and again across nearly 3 decades, using its extraordinary resolution to track the explosion's structure in a level of detail that would have been unthinkable to the astronomers who first spotted it in 1987. Most stellar explosions are observed once, maybe twice, before they fade beyond detection. This one has been observed for a human lifetime, and it is still not finished. Then, in the years since, something else happened, something that reframed the entire idea of watching a star explode in slow motion, this time in a completely different galaxy. In early 2018, an amateur astronomer named Koichi Itagaki spotted a new point of light in the spiral galaxy NGC 2525, roughly 70 million light-years from Earth. It was catalogued as SN 2018 GVOV. Professional observatories moved quickly, and Hubble began monitoring the object not long after discovery. What Hubble produced next was unlike almost anything the public had seen from a supernova before, a genuine time-lapse, stitched together from real observations taken over roughly a year, showing the explosion visibly brightening and then fading, image by image, like a flower blooming and wilting on camera. For the first time, people outside the research community could watch, frame by frame, what a dying star's light actually does over time, instead of reading about it in a paper months later. There is something almost unsettling about watching that sequence play out. A single point of light, easy to miss against the sweep of a spiral galaxy's arms, swells over a matter of weeks until it briefly rivals the brightness of the galaxy's own core, then begins the long, uneven process of fading back into the dark. Compressed into a short clip, it looks almost gentle, almost quiet. Stretched back out to its true timescale, it represents the complete disintegration of a star that had existed in some form for longer than human civilization. Meanwhile, on the other side of the sky, researchers studying a different, much older galaxy were reconstructing a similar death using an entirely different technique, one that didn't rely on watching an event unfold in real time at all, but on reading the aftermath frozen into archived starlight. Astronomers classified SN 2018 GV as a Type Ia supernova, a specific and unusually consistent category of stellar explosion. These events happen when the exposed core of a dead star, a white dwarf, either collides with a companion or pulls enough material from one to trigger a runaway wave of nuclear fusion. The white dwarf is obliterated. And because the physics governing that detonation is remarkably consistent from one instance to the next, Type Ia supernovae reach almost the same peak brightness every single time. That consistency is not a footnote. It's the reason cosmologists call these explosions standard candles. If you know how bright something truly is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. Type Ia supernovae let astronomers do exactly that, across distances so vast that almost no other method works as reliably. It was precisely this technique applied to supernovae like these that first revealed the universe's expansion was not slowing down under gravity, as everyone assumed it should be, but speeding up. That single discovery, built on dying stars used as cosmic measuring sticks, is part of why physicists now believe roughly 70% of the universe is made of something we still cannot directly detect, an invisible pressure researchers call dark energy. A slow-motion supernova, in other words, isn't just a spectacle, it's a ruler for the universe itself. But the story of a slow-motion explosion goes one level stranger than a time-lapse or a decades-long afterglow. And this is where a small, patient act of archival digging turned into one of the most unusual observations Hubble has ever produced. An international team of astronomers, working not with new telescope time but with old Hubble data already sitting in the archives, went looking for transient events, objects that appeared briefly and then vanished, the kind of signal easy to overlook in a single frame. What they found was a supernova located behind a massive galaxy cluster called Hubble 370, more than 11 billion light-years away, exploding when the universe itself was less than a fifth of its current age. That alone would be remarkable. A supernova from a period of cosmic history so early that most of the galaxies we can see today didn't even exist yet in their current form. What made it almost impossible to believe was this: in a single Hubble snapshot taken on one day in December 2010, the same explosion appeared 3 separate times. 3 different moments of the same star, dying, captured in one photograph. This is not science fiction, it's Einstein. General relativity predicts that a massive object, like a galaxy cluster, will bend the space around it enough to warp and magnify light passing nearby, a phenomenon called gravitational lensing. In this case, the cluster Hubble 370 sat directly between Hubble and the distant dying star, and its gravity split the star's light into multiple paths on its way to Earth. Each path was a different length. Light traveling the longer paths took longer to arrive. The result was a single Hubble image containing the same explosion at 3 different stages of its life, because the universe itself had, quite literally, delayed parts of the picture on their way here. For the first time, researchers could study how a distant supernova brightened, peaked, and cooled, not by revisiting the object over days or weeks, but by reading the differences frozen into one frame. From that, scientists were able to estimate the physical size of the star before it died, a red supergiant with a radius roughly 500 times larger than our Sun, one of the first times astronomers had ever measured the size of a dying star from so early in cosmic history. Everything changed with that single photograph. but the idea that gravity could split one explosion into several didn't begin with Able 370. It began decades earlier with a Norwegian astrophysicist named Refsdal, who proposed in the 1960s that if a supernova ever happened to explode directly behind a massive foreground galaxy, its light could be bent into multiple separate images, arriving at Earth at different times, and that timing those arrivals could be used to measure the expansion rate of the universe itself. For 50 years it stayed theoretical. Nobody found one. Then, in November 2014, working through the Hubble Space Telescope's Frontier Fields program, astronomers examining the galaxy cluster MAX J1149.5 plus 2223 spotted something nobody had ever confirmed before: 4 separate images of the same exploding star, arranged around a foreground galaxy in a rare geometric pattern known as an Einstein cross. The cluster's gravity had taken one explosion and split its light into 4 distinct paths, each one a different length, each one destined to arrive at a slightly different time. Researchers named it Supernova Refsdal, after the man who had predicted the phenomenon half a century earlier and never lived to see it confirmed. This is where the story stops being just an observation and becomes something closer to a test. Because the astronomers studying Refsdal noticed something else. The galaxy it exploded in was itself being lensed by the cluster, appearing in multiple locations across the field. If the models of the cluster's mass were accurate, that meant there should be a 5th image of the same supernova on a completely different light path that hadn't arrived yet. Teams of researchers built independent models of the cluster's gravity and made their predictions. Somewhere between late 2015 and early 2016, in a specific patch of sky roughly 8 arcseconds from the original 4 images, a new point of light should appear. Nobody had ever predicted the exact time and location of a future stellar explosion before, not once in the entire history of astronomy. On December 11, 2015, Hubble looked at that exact patch of sky. And there it was, a 5th image of Supernova Refsdal, appearing almost precisely where and when the model said it would, a star that had already finished exploding roughly 10 billion years earlier, sending one final scheduled delivery of its own death across a distance and a timeline that a small group of scientists had calculated in advance. It remains the first supernova explosion in recorded history whose reappearance was successfully forecast before it happened. The scientific value of that moment went far beyond spectacle. By comparing the actual delay between the images with what each competing model had predicted, researchers could test which model of the cluster's dark and visible matter came closest to reality, then use the timing itself to help constrain the Hubble constant, the number that describes how quickly the universe is expanding. It is in effect a second independent method for measuring the same figure that Type Ia supernovae like SN 2018 GV are used to measure, arrived at through an entirely different physical process, light delayed by gravity rather than light dimmed by distance. 2 completely different techniques, 2 completely different kinds of exploding stars, converging imperfectly on the same fundamental number describing the expansion of everything. Because if gravity can act as a natural cosmic-scale slow-motion camera, replaying one explosion at multiple points in time within a single field of view, then somewhere out there, other lensed events may be doing the exact same thing right now, waiting to be found in data that has already been collected and simply not yet examined closely enough. That is the theory some researchers have begun to take seriously. That the universe itself may contain a hidden archive of repeated time-delayed explosions, visible only through the right gravitational alignment, and that a careful enough search through existing telescope data, rather than new observing time, could reveal supernovae we have technically already photographed without realizing it. It's a striking idea. Explosions we've already captured, hiding in plain sight, doubled or tripled by gravity, waiting for someone to notice the pattern. But before this turns into something bigger than the evidence supports, it's worth pulling back toward the ground. Gravitational lensing of supernovae is real, well-documented, and grounded in more than a century of confirmed physics. Multiple lensed supernova systems have now been identified since Refsdal's prediction was finally confirmed, and astronomers use them deliberately, not as a mystical shortcut, but as a genuinely useful tool for measuring cosmic distances and testing the rate of the universe's expansion. The idea that more of them are sitting undiscovered in archival data isn't fringe speculation. It's a mainstream, active area of research, precisely because it's such an efficient way to study explosions from the early universe without needing to catch them in real time. What is not established is any claim that these lensed replays reveal something exotic about the physics of the explosions themselves. The star behind MAX J1149.5 plus 2223 died the same way countless massive stars have died before and since. Core collapse, catastrophic implosion, a shockwave tearing the outer layers into space. So did the one behind Able 370. Gravity didn't change either explosion, it only changed how and when the light reached us. The mystery here isn't about a stranger kind of death. It's about how much of the universe's history might already be recorded invisibly in images we've already taken, and about how much of that record depends on nothing more exotic than mass bending the space around it, exactly as general relativity said it would a century ago. It's also worth being precise about what the Refsdal measurement did and didn't settle. The Hubble constant derived from its reappearance carried a wide margin of uncertainty, and different teams' cluster models still don't fully agree with one another. Researchers describe it as a promising, independent check on the number, not a replacement for it. The broader disagreement between different measurement methods, an unresolved gap in cosmology known as the Hubble tension, is still very much unsettled. Refsdal narrowed the conversation. It didn't end it. That distinction matters because it's easy in a story like this to drift from genuine wonder into unfounded certainty. The honest version is stranger than the exaggerated one anyway. Consider what these 3 case studies taken together actually reveal. Supernova 1987A shows us that even a single explosion, close enough and well observed enough, can keep evolving for decades, forcing astronomers to abandon the assumption that a supernova's story ends within a season. SN 2018 GVAV shows us that with disciplined, repeated observation, a star's death can be turned into something almost anyone can watch and understand, a genuine visual record of transformation playing out in near real time. And the lensed supernova behind Able 370 shows us that the universe itself, through gravity alone, is capable of doing something no camera on Earth ever could, photographing one moment in a star's death 3 times over, at 3 different ages, in a single frame, 3 different explosions, 3 completely different ways of watching something die in slow motion. And all of it captured by the same aging telescope launched in 1990 that most people only think of as a source of pretty pictures of nebulae. 12 billion years. That's roughly how far back in time Hubble's cameras have managed to look, when you account for both the raw distance of the earliest galaxies it has photographed and the light-bending tricks that gravity itself provides. Every one of those photons has been traveling since before the Earth existed in anything like its current form, through the expanding fabric of space, past galaxies that have since drifted, merged, or died, until it happened to strike a mirror in low Earth orbit at exactly the right moment for us to notice it.